Your laptop runs on logic that hasn't fundamentally changed since the 1940s. On and off. 0 and 1. Flip a transistor millions of times per second and you can do anything from streaming video to running AI models. But what if we stopped thinking about computation that way entirely? Neuromorphic chips work more like actual brain tissue than traditional processors. Instead of moving data back and forth between a separate memory and a processor, they process information where it lives. Neurons fire when they receive enough signals. Connections strengthen or weaken based on experience. The chip itself learns. Here's the practical difference. A traditional supercomputer solving a complex optimization problem might need to check thousands of candidate solutions and compare them. It's methodical but power-hungry. A neuromorphic chip approaches the same problem more like your brain approaches recognizing a face in a crowd. It doesn't analyze pixels one by one. It builds up a pattern match across the entire system in parallel, using just a fraction of the energy. Companies like Intel with their Loihi 2 chip and IBM with True North have built hardware where each artificial neuron is actually a physical component. When you're running a workload that fits this architecture, the speedup is dramatic. We're talking 5 to 100 times faster on certain tasks while consuming 1/100th the power of equivalent traditional processors. The catch is specialization. Neuromorphic hardware excels at pattern recognition, robotics control, and sparse data processing. It's not great for the kinds of dense matrix math that powers large language models. So we're not replacing all supercomputers tomorrow. What's happening instead is hybrid systems. Data centers are starting to use neuromorphic chips for edge processing, sensor fusion, and real-time decision-making, then send refined data to traditional servers. This splits the workload in a way that plays to each system's strengths. The bigger implication is architectural. Computing has been built around the von Neumann bottleneck for 80 years. Moving compute and memory closer together isn't new, but doing it in a way that mirrors biological systems is fundamentally rethinking what a processor should be. As workloads become more about processing streams of sensor data rather than batch calculations, neuromorphic design becomes less of a niche and more of a necessity. If you want to understand how AI actually runs on edge devices, we've covered that already on the channel.